Welcome to Spring LIB.
Hi, we have been solving in some previous problems about some situations where you know certain components of velocities and then you figure out the angular velocity and the net velocity of a point. So let us look at another very practical situation and where we might need such kind of skill. So imagine you have a satellite and you have certain points, let's say A, and then let's say 4 feet below A and slightly offset. So somewhere here we have point B, and then offset from B and slightly lower we have some point C. So this is point C. Should write it here. So now on a satellite you might place some velocity sensors which are unidirectional, so they only measure the velocities along certain directions. So let's say VAX is 2 feet per second, VBX is, so these are only different components because a unidirectional sensor will measure the velocity only along certain directions. So this is minus 0.333 feet per second. And then for C, you have a y direction velocity sensor and it reads minus 2 feet per second. Now, can we figure out the total angular velocity and the velocity of point B? This is the problem. So let us try to write down all the distances. So from A to B, we have total of 4 feet. And then from B to C, we have total of 2 feet. And then the horizontal distance between A and B is 2 feet. And the horizontal distance between B and C is 6 feet. Okay. So as I said, most of these problems can be solved just by the basic principle of breaking them into translation and rotation. And the remaining of the problem is just finding out distances, angles, and taking the correct components and equating the correct components. Okay, so let us draw the diagram. So the motion is only in XY plane for the satellite. This is a given. So let us assume some translation of velocity Vt. And rather than drawing this complicated diagram, let's just draw a simple diagram with points A, B, and C. And let's assume all of them have some Vt in this direction. So it may not necessarily be in this direction, but once you solve the mathematics, you will get correct X and Y components for Vt, and you can figure out what is the actual direction. But you can always start by assuming some direction. And if the component is in some other direction, you will get negative of that number. So mathematics always saves you. So as long as you are consistent in everything. So let us assume this configuration for Vt. And let us assume that the angular velocity is like this. It's going clockwise, so it's pointing into the page. Then at point A, and let us B look somewhat in the center, so let us take B to be fixed. So we will call this fixed. And if angular velocity is like this, then this is our center. So this is our r vector. So the radial velocity omega cross r is going to point perpendicular to this r vector. And if my object is rotating this way, then radial velocity Vr at A will be like this. This will be omega and then distance between A and B. So let's call this DAB. And then about point B, you have velocity, angular velocity 0. Sorry, the radial velocity 0, angular velocity is always omega about all the points. And then at point C, this is A, this is B, this is C. So at C, if the object is moving like this, at C, you are going to point perpendicular again to this vector. And here the radial velocity, let's call this VRA, this is VRC, equals omega T PC. Okay. Now, we can add the known components and make them equal to the known velocities. So what is VAX? So VAX, this is going to be equal to this is 2. Let's just drop the unit for now. We'll put them back in the end because everything is in feet per second and all the distances are in feet. So VAX is 2, and then this has to come by breaking the component of A along this theta and also breaking this component of VRA also along this direction. So let us call that angle theta because Vt is not known, but this angle can be figured out. So we join the line A and B in this diagram, and this is where our radial velocity is going to point out. The distance AB, DAB, is going to be square root of perpendicular square plus base squared. That's from Pythagoras theorem. So that's 4 squared plus 2 squared. So because these are the right angle triangle, and this is 4, and this is 2, if this is A and this is B. So DAB will be given by 16 plus 420, square root of 20. We can write it as square root of 4 times 5. 4 can come out of the square root, so it will be 2 omega square root 5. So this is the magnitude, and along what angle are we looking? So we want to find out the x component. So we are looking at this theta. If this is theta, then this is 90 minus theta. And since this line is parallel, so this angle is also going to be theta. So if we look at this right angle triangle, we need cos theta component of this because this is going to be VTX plus VR at A cos theta from this diagram. The x component is going to be cosine theta, and we know that the total x component is 2 feet per second. So VTX plus this is going to give us 2. Okay. So cosine theta can be again figured out from this triangle. So we have already figured out this length is 2 root 5. This is 4. This is 2. Then cosine theta, and this is our theta from the right angle triangle we just drew. So cosine of theta is base over hypotenuse. So it's 2 over 2 root 5. So it's 1 over square root 5. Then our equation 1 is 2 equals VTX plus 1 over square root 5, that is the cos theta, and the VRA is 2 omega square root 5. So square root 5 cancels, and this gives us our first equation. Okay, now what are the other known components? So now let's look at B. So for B, there is no rotational velocity, but there is translational velocity. So at B, the x component will just come from VTX. So this will be minus 0.333 feet per second. So this is our equation 2. And you can already see that equation 2 is going to simplify equation 1, but we'll use everything in the end. So from 1, 2 equals, now we know VTX minus 0.333 plus 2 omega. So this tells us that 2 omega equals 2 plus 0.333. This will become plus after going left. So both are in distance. This is in feet per second, and I should have mentioned that this distance we calculated was in feet because these were feet squared. So this was feet. So this was feet. This is feet per second, and VTT is also feet per second. So feet all cancel. And just trying to make it look better, feet per second. So all the feet cancel, and then you are left with only 1/2 for omega, which is the correct unit because radians has no units. So this number is 2 times 1, then 1, 2 ones are 2, 1, 3, then 2, 6, then 1, 3 again. So 1.166, not feet, but radian per second. So this is your answer for omega. And we have figured this out by just equating the known components, taking translation and rotational components, and then equating the known components. So now we know VCY. So let us look at point C now. So at C, VCY is going to be VTY. So VTY, this was VTX, VTX. So VTY, and then this component of this along Y. And according to our diagram, this is going to point here, and we will need this angle, cosine of this angle, cosine of this theta. And what is DBC? So DBC, again, by Pythagoras theorem, we can look at the right angle triangle here, this right angle triangle. And in this right angle triangle, the perpendicular is 2 and the base is 6. So it's 6 squared plus 2 squared. This is 36 plus 4, that is 40. 40 can be written as, let's see, 4 times 10, which is 2 times 5. So 4 can come out. So this can again be 2 omega. And let's just leave it as square root 10. And this is in feet because these units are in feet squared. So this is our VRC. But we need the component of VRC along Y to equate it with VCY. This along added with the translation velocity will give us VCY. Okay, so what angle do we need? So we are at an angle 90 degree from line BC. This is the VRC, radial velocity of C. But we need the component along Y, which means we need the component along this direction. So we need this angle. If this is theta, then this is 90 minus theta. And if this is 90 minus theta, since this was perpendicular, this is going to be theta. Then let's just draw this right angle triangle here. So this is 2, this is 6, and we have figured out this is 2 square root 10. And this is our theta, and we need cosine of this theta. This is going to be b over h again. So this will be 6 over 2 square root 10, which is 3 over square root 10. Okay, now let us write down the equation for VC. So VC tells us that VC of y is minus 2 feet per second. So this becomes minus 2 feet per second equals, now this is going to be VTY, and then minus omega. So actually now I'm thinking, so if you already got omega, then all you need is the x component of velocity. Sorry, so the question asked us to find out omega and then velocity of point B. So we don't need actually, oh no, we do need this, sorry. So yeah, so VCY is minus 2 feet per second, VTY, because the other question asked us what is velocity of B, and velocity of B is going to be VTXI plus VTYJ. We already know this component, but we don't know this component, and this component is entering here. So that's where we get the other component from. Anyways, so this was going to be omega times 2 omega square root 10 feet. This is the VR, and then cosine of theta. Let me actually write this so that we do it in steps. So So this is going to be VR at C cosine theta, where the theta is some other angle. So maybe let's call it theta C so that you don't get confused. So theta C. And where else? At this point. So theta C. Okay. Right. Everywhere we have noted it. So cosine theta C. Now, so minus 2 feet per second equals Vty minus, we know that VRC is, we calculated it, VRC was 2 omega square root 10 feet, and then cosine of theta is 3 over square root 10. The square root 10 cancels, and then we can solve this equation for, and we also know the value of omega. So yeah, so minus 2 feet per second equals Vty minus 2. Omega is 1.166 and is feet per second times 3. So Vty is going to be, all these numbers will go here and become positive. So it's 2 3s are 6, and then 6 6 are 136, 6 6 are 36 plus 3 39, 6 1 is 6 plus 3 9, 6 1 is 6. So 6.996 feet per second minus 2 feet per second. So this is Vty. So Vty is 4.996 feet per second. So now you know Vty. We already know Vtx from equation 2 here. So now let's call this 3. So Vb is Vtx I plus Vtyj. So this is going to be equal to 4.996 feet per second I plus, okay, this is negative, so minus 0.333 J feet per second J. So was our diagram correct? We can just do a, so we have got all our answers, but as I said, you can assume any direction and eventually you get the right answer if you followed it consistently. So here we have positive X component and negative Y component, which is slightly smaller. So the Vt actually should have been pointing something like this, although we had assumed Vt to point like this. But as I said, once you get your final answer, you are going to get the correct direction of velocity, no matter what you assume. So that's how, even knowing one component of velocity, you can figure out angular velocity and velocity of basically any point you want, because once you have omega and you have Vt, you can just add Vt plus Vr at any point P to find out the total velocity. And Vt is going to be same for all points. That's the definition of rigid body, same for all P. So you can find velocity of any point once you know the translational velocity and you figure out omega. And then you can just take omega cross r of p and you can figure out velocities of all the points. So that's why in a satellite, or let's say you have some sort of device, you can just put these sensors which measure only along x or y, but still you can figure out the net velocity of any point. This is why these kind of problems are useful in real life. Thanks. See you in next problem.